you, folks. You spin me right round, baby, right round, like a record, baby, right round, round, round. You spin me right. I don't even know if you could hear my thing. Super loud. Nobody's home right now. Okay. Let's get out of here. All right. Woo! I haven't played any music in a while, and I was putting together these slides on rotations and particle on a ring, our next problem, and I couldn't get that song out of my head. You spin me right round, baby, right round. Okay, anyways, so obviously you can tell what we're getting into. Particle on a ring. Let's go, let's do it. So there's going to be a lot of things that we build from classical mechanics in describing the rotations of particles in terms of quantum mechanics. Okay, so the first thing I'm going to set up is our physical picture, this particle on a ring. Okay, and on this picture we have, notice our scale here, Z, X, and Y. We're going to be giving special attention to the Z-axis in this discussion because we have to choose one axis. As it turns out, there's going to be a little Heisenberg uncertainty principle going on. So we choose the Z-axis arbitrarily. Okay, so it doesn't matter. We've picked Z. So our particle is spinning around in this plane that goes in and out of X and Y. So it's rotating in the XY plane. Okay. So for now, we're going to say there's a 0 potential energy in that plane. So we only have to deal with kinetic energy. You can see now we've got the mass of the particle, radius to some center point. And then, of course, we have its linear momentum given by P. Okay. And, of course, its angular momentum given by J sub Z. So Z for the Z-axis. So you can see my lovely picture here reminding you of the right-hand rule and the cross product. So that X right there, right, that's the cross product, P cross R, okay? So if you look at here, the way this is notated, the A and B vectors, okay? So I always have to kind of think about this for a second. Yes, so A, my pointer finger, that's gonna represent the linear momentum. Okay, notice that it's tangential to the radius. And so then my middle finger is the radius. And if I rotate as the picture is showing, my thumb points in the direction of the angular momentum. Okay? So you notice here that angular momentum is plus or minus P cross R. And it's plus or minus because now, right, if I want to start spinning in the other direction, my angular momentum, right, is now pointing in the opposite direction. It's pointing towards the negative Z. Okay? Excuse me. Okay, so continuing along. We know kinetic energy is P squared divided by 2m. That's something we've talked about quite a bit, right? That comes from 1/2 mv squared. We know, we've just talked about that angular momentum is plus or minus P cross R. And then also we're going to take advantage of the moment of inertia, I equals mr squared. Okay, so this is all from classical mechanics, and this is helping to build our picture so that we can build up an operator and then eventually solve a Schrodinger equation for this problem. Okay. So let's see. I think I've talked about everything I wanted to on the slide. So let's keep going. So continuing along. Okay, so putting together our equations here, still dealing with this classical mechanics world. So we know that if the kinetic energy is P squared divided by 2m, and we're only dealing with kinetic energy, right? There's zero potential energy. Then I can rewrite my energy, kinetic or total, right? It's the same. I can write that as the following. So I recognize that the momentum squared, I can write that as jz squared divided by r squared. Okay, so I substitute that result in, and I get the following. So the energy is going to now equal the angular momentum squared divided by 2 mr squared, and we know mr squared is moment of inertia. So we're going to see this as our kinetic energy for this particle on a ring, jz squared divided by 2I. And we should keep in mind that this is still all classical. We haven't put any quantum stuff on this, right? This is just a particle spinning right round, baby, right round. Let's add the quantum touch to that, okay? And so the quantum touch that we're going to add is the de Broglie wavelength. So we remember now that in the quantum world, momentum is h divided by lambda, where lambda is the wavelength of our particle. It's the associated wavelength of the particle, which has wave-particle duality. So let's smash these equations together.